session. We have 4 speakers. It was Victor Gorbenko, Mehrdad Mirbabayi, Kostas Skenderis, and then Daniel Green. So I was going to start with Victor Gorbenko, but it doesn't seem like he's actually in the chat, although I see Leonardo is the collaborator. Mehrdad, are you here? Since you'd be next.
Hi, yes, I am here.
Okay, so yeah, I'll try and give everyone equal time, but if you just want to start with a quick summary, if you wanted to share any slides, you should have the permissions to do that. And then, yeah, like a 10 to 12 minute discussion for any questions afterwards.
Can you see?
Yes.
Oh, okay. So I basically try to study the same problem as the one that Matt described, except that I tried to study it in the static patch of the seater, while Matt was studying, or I think almost everyone studied it, starting from Stravinsky, studied the problem in the expanding patch of the seater. While I'm studying on in the picture on the right, which is the static patch. And one reason for it was that this is the intermediate object that you are working with, this average field. And the picture on the right is something that someone is observing. So I thought that is the nice feature of this change of perspective. Of course, the invariant questions that one wants to ask are the exponents of that equation, which give us the long time behavior of the system, or the long time or long distance correlation lengths. And those exponents will be invariant or independent of how I set up the problem. So I am basically formulating another way of calculating the correlation distances in the same problem, when I have a light scalar field in the seater with self interactions. And then I guess one other reason that I thought it's a good idea to think about or study the problem in this way is that once the object that we are talking about is the reduced density matrix of that observable phi in the static patch. And if I want to calculate just the equilibrium distribution, it's basically essentially follows just from this picture. The equilibrium distribution is given by, well, it's the diagonal element of the reduced density matrix that just follows from a sphere path integral. And that sphere path integral gives the famous result e to the minus v without needing to go through any kind of detailed calculation of the evolution. But of course, one is interested to also find the evolution equation for this reduced density matrix, or the diagonal element of it. And one can do this, one can set up a perturbative calculation for deriving that equation. So this can also be done in the static patch. And derive this well-known result for that reduced density matrix. I think the other question that I was very much interested in, and so this equation I could derive, but one thing that was left open in my first paper in last November was that, as Matt mentioned, this equation is a Markovian equation. And you can derive it, but I think it's a remarkable property that this equation is Markovian. because what we are doing is that we are talking about the reduced density matrix when we have integrated out infinitely number of infrared degree of freedom, low frequency degree of freedom. So it's normally one wouldn't get a Markovian evolution when tracing over soft degrees of freedom. So this was the thing that I thought it needs to have some simple reason to justify, because we want to make sure that it's gonna be true even beyond the leading order in perturbation theory. So basically the next goal was to come up with some general argument of why this is gonna be the case at orders. What is the principle and the technical reason that it's gonna happen? Essentially going to this next to leading loop order that Matt was talking about. Are we sure that we are gonna keep this Markovianity once we go there? Okay, so there is some intuition behind this. The intuition is decoupling of, if you go to the usual picture of a Stravinsky, is the decoupling of superhorizon modes and the short memory of the modes of the UV modes that give this diffusion term. So there is, and this intuition, I think it became very concrete in the work of Victor and Leonardo. At the level of the wave function, I think one can see that simple technical reason why it manifests itself to all orders in the perturbation theory. So I wanted a similar thing in the static patch. See what is that reason that allows me to get this local evolution to all orders. And I think I now understand what is happening. So essentially the structure of the interaction terms in the static patch is that the interaction is now depends, there is no translation invariance in the static patch, and the interactions are localized near the origin. And then we are at finite temperatures. So a bunch of this, essentially these two reasons lead to this property that once we talk about this calculation in calculation that again Matt mentioned, but of course now I'm doing it in the static patch, analogous thing, but in the static patch, the ingredients, the building blocks of this calculation, which were those commutators and anti-commutators that Matt mentioned, they have some universal late time behavior. So one can subtract or resum that universal behavior, and every deviation from those, they exponentially go to zero. So essentially the perturbation theory will be in these deviations from the universal behavior, which can be done order by order at leading order. So there is some diagrammatics of how to do it. So at leading order, they give the usual Stravinsky equation. And then at subleading order, one can find the corrections to the equations. We get some exponents that there is agreement with Victor and Nardo, and these allow, for instance, to calculate the corrections to the exponents. Okay, and this is the summary.
Thank you, Mehrdad. Sorry, so where in your setup are there like IR divergences of the kind that Matthew talked about showing up? I think I missed that.
Yes. So basically, imagine if you try to calculate, so this O operator is time derivative of this phi to the nth. Imagine you want to do some perturbative calculation here. What you will see is that this all terms of this this expansion are going to be relevant. Essentially, the anti-commutators and commutators of phi, they do not decay in time. So basically, you get factors of t to the n, as Matt says. So the same issue appears here. This secular growth in time.
Right.
If you want to just perturbatively calculate this, it fails. Yeah, I guess that's the probably.
Yeah. Okay. Yeah. I guess I was confused about how you get around it or where you regulate this if you needed to.
Oh,
but
well, I don't calculate them. That's exactly the point. This needs to be taken into account non-perturbatively. So what I do is that so the point is that essentially what happens is that there is only a single IR degree of freedom that is relevant, which is essentially this phi bar, and everything else has short range interaction. So what I do is that I separate phi bar and I keep it non-perturbative, but every deviation from it has a short range interaction, and that can be calculated perturbative. So for instance, when I draw this diagram, I'm doing like some simple first order calculation, but this result will be dressed with all of those commutators to turn this interaction picture field into the full field.
Okay.
Hi.
Is it another question?
Yeah. Hi, Mehrdad. In your analysis, you assume gravity is non-dynamical, and then you found that the evolution in the static patch up to the leading order is Markovian. However, my understanding is that in the 4-point Poincare patch, we start from one vacuum, and then very slowly we evolve to another vacuum, and then this evolution can be captured by BMS group super translations, which would be missed if we consider exact de Sitter, but one should consider asymptotic de Sitter and the fluctuations on the top of that. Do you have any comments about that? I mean, my expectation is that if one assumes asymptotic de Sitter, that the memory effects or deviation from Markovian evolution might show up. Do you have any comments about it? Thank you.
Yeah, I guess I can say, well, the first thing that I should say is that for me, gravity is non-dynamical. Eventually, one would want to turn it on, and when you understand just the field on the Sitter background and see that there is no crazy growth, everything is regular, then one would expect that after turning on gravity, nothing dramatic is going to happen, again, as Matt emphasized. I should say that when I say memory, it's not very much related to the memory effect that you might have heard in other contexts, especially when people talk about the BMS group. This has almost nothing to do with that. I'm just talking about these short-range correlations, or basically, when I say memory, I'm just talking about this Markovian evolution. Markovian evolution, as you see here, is an evolution that doesn't have memory. At any time, given the distribution at that time, you can evolve it forward. So that's what I meant by memory.
Great. So,
or the loss of the memory.
So thank you very much, Mehrdad. In the interests of time, let's move on. So I think Victor is here now, and I know Leonardo is.
Yeah, I'm here.
Okay, great. So if you wanted to very quickly give a brief summary or show a slide or two,
Sure,
just
yeah,
to
I
recap
can.
your talk.
Yeah. Am I allowed to share the screen already?
Yeah, you have permissions. Yes. Yeah, then I think people are interested in
Okay.
hearing comparison and contrast
Yeah.
between your work
Yeah,
and the work of
well,
Matthew and
okay.
Mehrdad. Mhm.
So what is okay? So the just the one of the summary sort of the results slides of the presentation that I used for this talk. So what's the conclusion? There is this issue of infrared divergences that was written many times. I'm not going to repeat it today, but the point is that okay, in quantum field theory it's solved. How is it solved? So in order to compute correlation functions, it is a little bit of an involved procedure, but the main point of the talk that this procedure, there is nothing conceptual that is left unknown about, okay? So you define these objects that are denoted by P here, and again, we have a sort of rigorous definition of it, of what this object is. And these objects P, they satisfy some of linear differential equations that are written here. So there is some time evolution is equated to some partial derivatives with respect to field values. Okay, and what is actually written here? So this differential operator is gamma, defined above. Again, we can go into details what these operators are, but these leading operators gamma, they were already defined by Starobinsky, right? And it was shown that this leading part of the equation, that has some nice solutions, time-dependent solutions at late time approaches some sort of attractor solutions. What we did, we showed that, okay, there is no problem in deriving this sub-leading operators that here are denoted by D. Again, I don't, on this slide, I didn't spell out exactly these D's are, but the main point is that there is no, we can, if we want, we can calculate these D's to any order in perturbation theory that we like, okay? There is no more issue of infrared divergences left. Now, anticipating some, well, basically I can repeat the answer to questions that were already asked to Mehrdad. First of all, what's the difference? Why is it a different approach? We focus on calculating correlation functions, again, for now in field theory, but at any points in the zeta space. So it could be points localized to a static patch, as Mehrdad's formula works, could be points localized on the equal time sort of inflationary part, inflationary patch somewhere, you know, late on the reheating surface, can be arbitrary points in the zeta space, arbitrary endpoint function. The formalism works, okay? Then next, where did infrared divergences go? Okay, so this is a set of linear partial differential equations. Now, it turns out that if we focus on this leading part that contains differential operators gamma, for example, let's just for a second focus on the equation for the 1-point distribution. Okay, just DTP is equal to gamma 1 P1 in our notation. Here a little bit spelled out, a little bit more in leading order in the coupling constant. So this lambda is not coupling constant. This lambda is what? It's eigenvalue of this differential operator. You see here, it's here to leading order. It is a second order differential operator like Schrödinger equation. So now this differential operator, its eigenvalues and eigenfunctions have to be found non-perturbatively. This is where the entire strong coupling of this problem went. So maybe here I have a little cartoon. So what happens is that when we solve these partial differential equations, okay, so this is just to repeat, the problem of resumming Feynman diagrams or whatever approach we use to calculate correlation functions was reformulated as solution of some system of partial differential equations. Okay, so now, what is the physics of this partial differential equations? It's not some abstract differential equations that I know we just read it. They're very physical, what they describe. So now this is a cartoon of what these partial differential equations describe, okay? So suppose we want to calculate some 3-point functions. So here we put 3 points somewhere, say this is a reheating surface, for example. 1, 2, 3, okay? So what happens is that first we go very far in the past, okay? And very far in the past, these points, when they go deep inside the horizon, they evolve together. And their evolution is described by evolution of this single field differential operator gamma, or like gamma 1, we call it. And this needs to be solved non-perturbatively. Okay, but this is just single degree of freedom at this point. So we're just solving some single differential equation non-perturbatively. We can do it. Now, at some point, when say point x3 goes out of the horizon as compared to points x1 and x2, that, for example, are closer together. Okay, and this picture not very good, but say x1 and x2 are closer than x3. So x3 separates. Now, there is a short period of interaction between this field at point x3 and this joint field at point x1 and x2. And that's where these differential operators, this differential operator D, this differential operator gamma 1, 2, that's where it comes in, and that's where it needs to be taken into account. But that can be done in perturbation theory, okay? Then again, separately, the point 1, 2, and 3, they evolve in this strongly coupled manner. But this again is an independent degrees of freedom, one field, one sort of like one particle, one quantum mechanical degree of freedom, so we can solve them independently. And the same thing happens to x1. So this is the dynamics. Again, this is very physical. This strongly coupled evolution of a single degree of freedom, if you will, like inside the horizon, that also Mehrdad's approach described. Then this separation of degrees of freedom when they cross the horizon, the corresponding mode crosses the horizon. That can be described in perturbation theory. And then again, independent evolution of degrees of freedom that are already outside of the horizon and don't talk to each other anymore. So this is what the physics of this set of differential equations. And again, just the question was asked to Mehrdad, what happens with gravity? So this, what was worked out carefully, that is without gravity, quantum field theory. The new subtlety with gravity that already I bragged about on Monday is that to get something well defined, you need the inflaton. Okay, if there is no inflaton and there is gravity, I do not, maybe somebody else, I do not know how to define correlation functions. If there is an inflaton, some inflaton means for me what? Preferred time slicing. If there is preferred time slicing, then we can define correlation functions on these preferred time slices and using as a spatial distance, for example, geodesic distance, or I mean, to leading, or if you want to go to some a leading, or maybe even some few leading orders in perturbation theory, you can get away with some simpler prescription. But anyway, yeah, let's say we define correlation functions with space like geodesic distance pins to the reheating surface, and then the same formulas can be applied. Same set of equations can be worked out. There will be corrections to these differential operators that go with h squared over m Planck squared. But okay, the detailed form of these corrections still we haven't written it down. But again, conceptually, there is nothing that you need to sit and think what to do. You just need to calculate.
Right. So
maybe I can take questions. I mean, I can explain more details, but maybe I should just.
Yeah, there's just a few minutes left, and I think there will probably be questions. So yeah, let's try and use the rest of the time maybe for discussion. So yeah, are there any questions for Victor or for Leonardo, or Leonardo? Did you have any?
No, maybe I can add a couple of things. Maybe do you hear me? Yeah. Maybe I can add a couple of things addressing some specific questions that were asked before. So I think these three pictures that Victor showed is maybe the answer to Nima's question about hard process. Okay. Then quantum effects are, we also, I mean, of course, Victor didn't explain because it's time and also because they're very small, but the quantum effects are also included in this formalism. We can compute them. Given a Lagrange, we can, given a specific Lagrange, we can, also the quantum effects can be included. And it's really formulated as an effective theory. That is, this what we got discussed is the theory of the long modes, but the full theory is the theory of the long plus the short. We split the theories, and one solves both, and then joins and combines the answer to define observables. And this is crucial for subleading orders. So this I wanted to just to say schematically, because I think each one addresses one point was discussed before.
So actually on this point, something that Matt brought up in his talk was about how the split into long and short, it's very similar to like the real method of regions, method used a lot in field theory. But I think in your paper, you used more like, some smooth interpolating function that shuts off long modes versus short modes. But did you try?
Yeah, that's a technical detail. Yes.
Yeah. Right. Does that matter? Did you think at all about using a more
actually we use two. We use two. I mean, one we use.
We saw. So basically, why? Okay, so here it's on this slide. It's explained briefly that actually you need to when you do the separation. So that's the definition of the long field. Okay, so again, you go in momentum space, and then you convolute it with this. Okay, here I had theta delta, which is like heaviside theta function, but it's smeared. Okay, so it's 0 for very short modes above this cutoff lambda, this de Sitter invariant time-dependent cutoff lambda. Now it is exactly 1 for modes much shorter than lambda, and then it interpolates in some momentum shell of width delta. So delta is in a sense another expansion parameter. Why is this convenient? Because if you take, as say, Stravinsky did, if you take a sharp theta function, then to leading order in perturbation theory, you get exactly the same thing. Perturbation theory means perturbation theory in little lambda in coupling constant. Now, in subleading orders, even at just the next to leading order in lambda, you start seeing a difference. You start seeing the following effect: that if you take a sharp cutoff in momentum space, you lose locality. You lose locality in position space. Not so surprising, right? Doing some sharp manipulations in momentum space, you lose locality in position space. Now, as you saw, our equations, they work point by point at position space. So you actually lose this property that points that are outside of the horizon do not talk to each other, just because you did some formal manipulation to your theory that completely broke locality. So even, fields outside, infinitely far away from each other, they still formally interact with each other. So to avoid this non-physical effect, you do the smooth cutoff, and then it completely goes away. So now we showed in some appendix of our paper, you can see that if you insist on working with this sharp cutoff, that technically becomes a little bit simpler. You can take into account this non-local interaction, and you get the same answer. We checked explicitly to some orders, you get the same answer. So you can do either. It depends on in what your taste is. If you want to use sharp cutoff, or if you want to use the smooth. The smooth cutoff is a bit more physical, right? More intuitive, because you don't have this non-local interaction. But if you want this non-local interaction, can be derived again to any order. So either works.
So I think we have time for maybe one more question, if there is one. Whoever can just speak up.
Yeah, could I actually this question of the need for a cutoff to distinguish hard and soft is exactly where the sort of the distinction in the formalism is, just in the formal level with what I did with Matt Baumgart. It's very much like saying you do calculate Feynman diagrams in Minkowski space, and ours is a little more in the spirit of resumming large logs, infrared logs. Okay, so just resumming infrared logs without having divided into UV and IR. And and the spirit of what you guys are doing, you know, it's a generalization of the spirit of this, as you say, the sort of the Polchinski or even Wilsonian idea that you just imagine, at least imagine a cutoff in that sense.
Yeah.
But I did want to ask, in the case of like the soft cutoff, the smooth cutoff, again, when we were contemplating which choice of weapons to use in tackling this problem, for us, this business of what's happening right around the cutoff region was always indeed not just technical, but just conceptually the thorny thing. And so at least in the soft cutoff, you say that it gives rise to sort of only the cutoff or the regulator is still seen as a kind of a local effect. Is that right? Even
yes,
the hard cutoff, that the sharp cutoff, that you have a non-local thing.
Yeah, exactly. I think you summarized correctly. Again, okay, we can. I know I didn't put it on the slides. You know, it was impossible. It gets technically. I was surprised when we were working this with Dana. I think both of us were surprised how quickly it gets. You know, just the equations get long. That was a little bit even surprising. So this, I couldn't put them on the slides, but okay, if you want, maybe privately we can go through, you know, appendices and paper. Yes. We did.
I'm willing to take a statement. I don't even need the proof. I just want to know.
Yeah. But statement you summarized, I think, very carefully. Yes, if we work, there are interesting physical effects that happen around the cutoff surface. So basically, there are terms in these equations. Okay, these d terms that couple different points that depend on the details of how we do the cutoff, okay? And if we do the cutoff in a sharp way, then there are these terms that couple different endpoint distributions in a way that, you know, doesn't decay fast when x goes to infinity, or physical distance goes to infinity.
Right.
In the case of a smooth cutoff, those terms are absent. Instead, there are some terms that are important when this distance, or physical distance, right, x times a, is around the cutoff scale. So when this distance is around cutoff scale, there are some terms in here that depend on the details how we do the cutoff.
Yeah.
And that's because these p's, they depend, their definition and their value depends on how we do the cutoff. Once we compute the physical correlation function that, as Leonardo emphasized, is a sum of short and long correlation functions, the cutoff dependence goes away, and also this little delta, which was the width of the cutoff surface, also that dependence goes away. Yes, and I think the same happens for Polchinski. Polchinski also doesn't do a sharp cutoff, right? It's important, and it's part of the paper that he does a smooth cutoff. But of course, again, if we hit the exact RG, nothing depends not on the value of the cutoff, but okay, also on the shape of the cutoff function. You know, the exact relation function, they do not depend. Right?
Because the physical difference with Polchinski is that in Polchinski, physics at the cutoff is far off shell. You don't have the energy at low energies to excite actual on-shell degrees of freedom at the cutoff. So in some sense, you have a very blurry vision of them in your correlators.
Yeah.
Here, you actually have modes going right through your cutoff region, and they keep coming. So they keep physically sensing however you did the cutoff. And the question, you know, if I have your equations on the board that are on the slide here, then I'd say, yeah, that looks good. The question was deriving these equations, and was there any obstruction from the fact that UV modes are constantly passing exactly through the cutoff region on shell? That was the question.
Well, yeah, so there is, there isn't that sharp of a notion of, you know, on shell versus off shell in this, because we are computing correlation functions. So indeed, if we were just to compute correlation functions of long fields, right, they depend on the cutoff and on the details how the cutoff is defined, as they should, because there's objects that are definition of these operators depends right, okay, where is the definition? Here, right? The definition of this object depends on how we do the cutoff. So of course, if we just compute the correlation function of phi long, it would depend on these details. And I think this is the problem that you're pointing out. It's true that in some sense, if we just take a very long distance limit of correlation functions, it's only the phi longs that give the leading contribution. So that's how we can easily forget about these details, which is basically what Stravinsky, he didn't care about how he precisely defines the cutoff. But yes, if you go to sub-leading order, then you need to compute the combination of phi long and phi short. And there, physically we understand, right? Once we compute phi long plus phi short, it shouldn't matter, right? How we separate them, because eventually we're summing up two pieces that there is a theta and its complement, which gives one, right? So at that point, all these details, they cancel out of the physical answer, and we observed it just in the calculations.
Can I add that?
Sorry, Vic, sorry, we need to move on. Otherwise, we're going to be really over time. But thank you very much, Victor and Leonardo, and everyone who participated. There's a discussion at the end where we can maybe add more. But so next, because it's on a similar or at least related topic, Tim Cohen, are you here?
I'm here.
Yes.
Share.
So no, Dan Green.
I'm also here.
Oh, you are here.
I
Great.
just
okay.
Okay.
Yeah, so
speaking of
Dan,
these issues of the cutoff, actually, we have another point of view on this.
Right, exactly. So I'd be interested in hearing about that for sure. So you have sharing permissions, Dan, if you want to very briefly share, one slide.
Okay. I mean, yeah. So
or jump into it.
Yeah, we can just jump into it. I mean, what we did was derive an effective theory for the long modes. So the procedure is to identify the degrees of freedom that are relevant when you're looking only at super horizon modes, and you integrate out all the short scale physics so that you can do power count. So the power counting works, the symmetries are manifest for calculating loops and how they affect super horizon modes. So that was our strategy. I think some of it's a bit technical, how you get there, but I think at the end of the day, you have 2 degrees of freedom, a growing mode and decaying mode. You have a local action for them, and you can do something similar to DimReg to calculate what happens to those modes, and sort of the construction of that was the point of my talk.
So I have an immediate question, maybe. I was a little confused about how much of the advances of your paper were in the EFT's separation of studying long versus short, and how much was just introducing this kind of version of DimReg to regulate loops. Like, could you have just done that in the full theory? And also
it's tough to do it in the full theory. So I mean, at the end of the day, so it's at some level, it's really that once you get to the low energy theory, you have scaleless integrals, right? So if you don't have scaleless integrals, even trying to do DimReg doesn't work, right? So DimReg doesn't. So this is a problem even with just doing DimReg in conventional inflationary calculations, is that if you have these e to the I k taus floating around, and those aren't scaleless, so you might have had a loop that now they bring down 1 over taus, and instead of something that normally you'd think give just 0, for example, in DimReg. And you're always tracing through that problem. But when you go to the EFT, now you just have scaleless integrals. You're integrating over powers of time, powers of momenta. And so you inherit all the nice features of DimReg. DimReg itself doesn't work very effectively in inflationary calculations as well. But this generalization has all these nice properties.
Yeah, okay. This generalization is also used a lot by like Kostas and Adam and Paul and in some of their CFT.
It's standard for doing Fourier transforms, right? It's like how you Fourier transform anything. It's not anything unusual. You're analytically continuing in powers, which again is what DimReg just does that in one particular way, but there's no reason it has to be dimensional. I mean, conformal perturbation theory, you do the same thing. You analytically continue in the dimensions of operators.
Right. Okay. Thank you. That'll clarify.
Maybe I can jump in and just say a lot of the conversation that's going on here, the way it's kind of recast in our language is there's a new ingredient for this kind of EFT, which is the need to specify initial conditions. And so a lot of I think the questions Raman's asking are, how do you specify those initial conditions? And then when you do matching calculations between the full theory and the effective theory, you also need to match to whatever order you're working at in those initial conditions. And so that is something that really distinguishes this from other EFT, more conventional EFTs that we're familiar with.
Are we asking questions, or is Dan continuing?
I think ask questions.
Okay.
Yeah.
I have a question.
Okay. Mehrdad, okay.
No, you can go.
Okay, let me ask you a
my
question.
question is why do you expect to have a local EFT for the super horizon modes?
Why do you expect to have a local EFT? So, I mean, different points of view will give you different intuition. I mean, we explicitly checked that integrating out the short modes doesn't give rise to non-local terms. I think your intuition would be that the production of particles happens as it's crossing the horizon, and then you're not producing non-local effects, right? So this is exactly what happens, as you know, in stochastic inflation, right? You have this noise that acts locally, but the noise doesn't act non-locally. The non-local information is in the initial conditions. So you do create non-local initial conditions, but once the modes are super horizon, different spots in space that are super horizons can't talk to each other anymore. And that, I mean, again, you can verify that by explicit calculation if you don't trust the physical intuition.
Yeah, but shouldn't I worry that non-locality in the initial condition somehow leaks in the structure of this EFT?
I mean, we're distinguishing time. So the time evolution is what the action is giving you, right? So the time evolution doesn't, I mean, that's there in the initial conditions for the field. So the initial statistics are there. You can then follow how those initial statistics evolve through time evolution, but the time evolution itself is local. That doesn't mean it doesn't give rise to non-local correlations, but it does mean that there's not no non-local dynamical effects. And that's all you need for a local action. Right? Like you don't have information propagating from one subhorizon region to another subhorizon region. That's the main reason that you don't have non-local interactions.
Yeah, can I ask my question? So my question is the following, which is, by the way, related to Mehrdad's question. So how efficient is your formalism in the following sense? So there is this Lakmus test, I think, of different formalism in particular for treating infrared divergence. Like if you take this lambda phi to the 4 theory that we all like, and you calculate the correlation function, but to a sub-leading order. Okay, to leading order, there is this Stravinsky answer, can be derived in a billion different ways. Then let's do the sub-leading calculation. Okay, so I know we did it, and say Mehrdad also did it, and we agree. Okay, there is some number, that showed up. So how is it feasible? At least in your paper, I don't think you calculated it. So how feasible is it to calculate it in your formalism?
So I guess I'm going to ask your question first. Are you talking about corrections to the equation for the
correction to the
taking Stravinsky and solving it?
No. So let's take 2-point function of lambda phi to the 4 theory. We take 2-point function at long distances. It behaves as x to some power. Okay, this power depends on the coupling constant of the theory, lambda. In lambda phi to the 4, it's lambda and the mass. Say we do m squared phi squared plus lambda phi to the 4. So it depends on m squared and lambda. So it's some function of those. And then we expand it in lambda. And the leading order is some, 1.13 times square root of lambda. That was Stravinsky calculated. Then the next order is like some other number times lambda, So this other number, like, can you calculate it?
So, I mean, we would agree with you that at the end of the day, to solve those equations, you're going to solve them using the same equation. So our equations for the...
Yeah, that is a question of deriving equations, if you like.
So now if you're asking about corrections to those equations, so we can calculate those efficiently. So for example, a number of your corrections that you calculate in our paper are determined by the field redefinition we'd use to remove our 5 plus to the 4 operator. And so all of those coefficients, the 1/9, 1/27, all of those, those just follow from the field redefinition. So we can get those right away.
Oh, okay.
We know that there's no gradient corrections. We don't have to estimate those. They're just zero. No gradient corrections. All of that stuff is immediately zero. So you don't have to worry about those kinds of terms. And so, yeah, like, could I worry that there's like a 9-loop diagram that introduces some effect? I mean, in principle, I could worry about that, but so we're still, which is like, can you prove some all orders results about these corrections? In the short answer, can we calculate affections efficiently? Yeah, because we're calculating logs. So it's no different than saying, does Polchinski tell you how to calculate the beta functions? No. Do calculating the beta functions tell you how to solve the Kalan-Szymanczyk equations to determine correlation functions? No. Those are
it's okay to calculate the beta function.
So
I guess that's what I was asking. But
so
you know UV theory that you can do the matching. But the reason that subleasing order is important because there are this many effects that's coming, right? For example, this thing that you said about, oh, there is no non-local interaction. Well, I think that's only true if you do cutoff in this smooth way, because if you do a sharp cutoff, I mean, look, if you do a sharp cutoff, it's like, let's say zero mode of the field. By definition, zero mode of the field, it talks, you know, it's on the whole space time, right? There is, for zero mode, there's interaction between points outside of the horizon, right? So you should also, I think, see it. Like,
yeah, but again, that's local. It means if I'm here and there's a long mode, I depend on what the long mode is where I am. Right? Now there's correlations because it's a long mode, but that doesn't change the equations. The equations still say the time evolution where I am in this spot depend on the value of the field in this spot and not on the values of this field somewhere else. Now, when you can decompose that into modes, indeed, you get loops and those involve those things. Now, I would claim that DimReg just makes a lot of those calculations much easier. And so the whole discussion about hard cutoff versus smooth cutoff, just many of those things are zero in DimReg, right? So, and again, I want to distinguish what we did from just saying we're only interested in the case of massless modes. I mean, what we did extends to any mass, any spin, and in many of those cases, all of this is trivial, right? Like, there's no interesting loops for fields, right? And like, that's not obvious even in the UV description, right? Because you have
I agree. I guess maybe I already did it, but I couldn't see it from the paper that they just, you know, just to actually calculate this subleading equations.
It's in progress. I can tell you what we know so far. I'm just saying we wanted to set up the formalism on one paper because the formalism applies very generally. It's not just about stochastic inflation. And so we're going to do the matching in specific examples at 1 and 2 loops to see to show you how it works in a paper that'll be hopefully ready soon.
Sounds great.
I had a question for Dan and Tim.
Go ahead. Last question, and then we'll move on to.
So just you know, so obviously, you know, as you know, I'm very sympathetic to your goal and your approach to the EFT and the sitter. The one thing about this problem that seems exotic from the point of view of just standard particle effective field theory are these fluctuations at the horizon. And to me, if I were to try to formulate a particle analogy, it would be as if I was trying to study the low energy dynamics of a particle theory, but I was coupling it to some thermal bath. But the thermal bath is precisely at the scale that I would want to call my hard scale, right? Hubble is a high scale from the point of view of the super horizon modes. So I was just wondering if you knew of any. It's just almost a proof of concept. If you knew of any other EFTs where that's the case, where you sort of where it's still tractable to talk about a low energy effective field theory, but you're always being whacked by high energy fluctuations, or maybe you're innovating and you see some way around this issue.
So I mean, Tim might have a better perspective of the space of all possible EFTs. I guess what my answer would be, and I'll throw it to Tim after, is just that, I mean, the effects that you're talking about, those ones are still visible in the EFT, right? Those are modes coming into our EFT, which is RG, right? So that stuff we see, and that's those modes crossing the horizon are modes at like within the regime or EFT. And the only question is, do those introduce logs, effects that build up over time, which is the same thing that you guys were looking at. Now, so I do think the novelty is, I don't know an example of an EFT. I mean, I think I want to distinguish, there's also an EFTs where you have initial conditions as part of the input, right? So large scale structure as an example, right? Like you have an EFT, but you have to specify initial conditions. And so what I would say is that this case just mixes those two things up. It's not obvious for you, maybe a priori, that those things can be absorbed most of the time into the initial conditions, except in the special cases where they give logs. But maybe Tim has a different perspective or an interesting example.
Tim, if you have something really quick, yeah.
I agree with everything you said, Dan. I mean, I think one thing that makes these calculations kind of unique, at least in my experience, is the fact that we're projecting on this, future time surface, and so the so there's not. I mean, propagation is kind of a different thing than we're used to when we think about just normal particle physics, and so for me, at least, that was kind of a retooling of my intuition and thinking about this with Dan was trying to understand those differences. And I think the question you're asking speaks exactly to that. And I think it's just captured by this way we incorporate initial conditions, and that we can systematically improve them through matching calculations, right? So it really follows the intuition that you have from typical continuum EFTs, right? You can just systematically improve everything in the matching step.
So who has the strongest, just one small thing, okay? I brought up this question earlier and I'm glad that it got aired, but who has the strongest cutoff on the size, the strongest infrared cutoff on the size of the equations, as Victor put it? I think that's what this latest debate was about. Everybody gets the same place, but the size of the equations is what you're now debating, if I understand correctly.
I think every group may have their own opinion on something like that.
I don't know, but that's what I asked, how hard it is to derive this subleading correct. I mean, in our approach with Leonardo, okay, it's hard, but we calculated, to some subleading order, so you can sort of see at least it's finite. Let's say the size of the equations is finite. That was proven, but. Can I make enough time? I want to.
Same answers, right? I mean, you guys are basically saying different RG schemes get the same answers.
Yeah, everyone agrees. It sounds like, but yeah. Sorry, Victor. Maybe there'll be time later, but we do need to move on, and there's been an additional talk we need to discuss too. So, on that note, we'll move on to a slightly different subject. If Kostas Skenderis is there.
Yes.
Yeah. If you want to share anything, very briefly, and then we'll start a discussion.
Okay, can you see the slide?
Yes.
Yes. Okay, so this is a different topic. It's more in line to what we discussed yesterday. So in the talk, the talk was based on two parts. In the first part, I sort of review the relation between inflationary correlators and conformal field theory beyond kind of the slogan of the sitter is the sitter group is the same thing as a conformal group in one dimension less, and I will briefly review this in a minute. And then the second part, I'm sketching the proof of that the simplex that Paul discussed yesterday solves the conformal word identities. Okay, so I think the connection between inflationary correlators and CFT can be established in a rather robust way based on very simple principles, kind of going also through the sitter and under the sitter. And I think it's based on something which I feel it should have been better known than it is. So the asymptotic structure, both of the sitter and under sitter, is essentially identical up to signs. So here I give it for 4-dimensional de Sitter or under de Sitter. So if sigma is -1, then this is for de Sitter, and if it is +1, is for under de Sitter. And it's basically determined by this, the kind of the black and the blue part. So in ADS CFT, this leading part is the source that couples to the dual operator, which is the energy momentum tensor, and this blue part is the piece which encodes all correlation functions of the energy momentum tensor. Now, by just using the fact that the bulk action has bulk diffeomorphisms, one can show that, and then this asymptotic, this more general asymptotic solution of the field equations, one can show that this blue part satisfy differential equations, which turn out to be identical with the conformal Ward identities in one dimension less. So since the sitter has exactly the same asymptotic structure and exactly the same set of diffeomorphisms, the same is true also for the sitter, or any inflationary background, which becomes asymptotically de Sitter. So this is the first connection. Now the second part is, of course, when we discuss inflationary observables, cosmological observables, we're really looking at the leading behavior, which is this G0 part. And here, so to connect the two, one needs to use what is the initial state. So what connected to one uses, this comes from the choice of the vacuum, for instance, Platch-Davis vacuum, and the Vronsky relations that follow from that. So that gives, without going much into technicalities, gives a direct link between kind of inflationary correlators, ADS correlators, and CFT. So this was part one. Now in part two, I wanted to establish that this simplex representation in momentum space satisfies the conformal Ward identities. So let me briefly describe this. So this was described also yesterday by Paul. So this is given by, so this expression is defined giving a simplex. So here is a simplex. So a simplex has the property that if you remove any point and all the sides connects it to the rest of the polytope, then you get another simplex, a lower dimensional simplex. So the correlator is defined by providing momenta at all the vertices of the simplex. So if you have endpoint function, you give the momenta, and then you provide internal momenta that connect each edge. And then this expression here is an endpoint function that satisfies the conformal Ward identities in momentum space. So in the next few slides, I'm just going to sketch how to prove that. So to prove that, I'm going to start with a slightly simpler expression. So I'm going to put this function f of u, which is the general function of the momentum space cross ratios. In the beginning, I'm just going to put it to 1. So then I have this integral, which we call a mesh integral. So this expression here satisfies a remarkable recursion relation. So if you're given two simplices, so here we have 4 simplex, then you add another point, you get, sorry, this is a 3 simplex, you add a point, you get a 4 simplex. So if you want to know the correlation function, the mesh integral for this expression, then it suffices to know the mesh integral for the lower dimensional one and just use the formula that I give over here. So given an expression for the mesh integral, you put it here, and then you do the integrals over the new internal momenta. In this case, would be Q1, Q2, Q3, Q4, and then you do this integral, and then you get the mesh integral in for the next simplex. Okay, so now the first step is to prove the conformal invariance for the mesh. So proving conformal invariance means that if you act with the generators of the conformal group, then you get an invariance. So for Poincare invariance is obvious, and then dilatation invariance is also very simple to show. So I'm just going to focus on spatial conformal transformations, which is the most complicated one because it's a second order partial differential equation. So to prove this, what we showed is that we showed that it's not only that the mesh integrals satisfy the recursion relations, but also when you act with the spatial conformal transformations, you also get a similar recursion relation. So now you can use an inductive proof. So if you know that the simplex in the n-1 simplex is conformal, then the nth simplex is also conformal. So you can prove that by induction. Now, once you've proven that the meshes are invariant by conformal invariant, then it's pretty much goes for free that you can add a general function of crosses, provided this is a twice differentiable function. And the proof is not simple, but given the time, I'm not going to go through it again, unless you ask me to go through it. Okay, that's it. Thank you.
Thank you. Any questions for Kostas?
Kostas, is the integral with f equals 1? Is it does it come from a natural space?
Yes, it does. Yes, it does.
Yes. Integral?
Yes. So it comes from it was on the slide, so let me put it.
Sorry, yeah, I missed that.
Yeah, so it's
in other words, is it conformal invariant obvious from some oh, I see, there it is. Oh, I see, it's just a Fourier transform of that. So that makes it clear that it's conformally invariant ab initio.
Yes, yeah. And you can also say, so these alpha parameters are exactly the same as this alpha parameters. These are related to the dimensions of the operators. Actually, this expression here is not just expression with f equals 1, this is an expression with any f, which is equal to a monomial raised to any power, because this is the set of solutions of these equations. That's why you can prove later on in a simple way that once you've shown conformal invariance of this expression, then you have conformal invariance of the general case.
Is it easy to see how like OPE limits work for your general expression and how things factorize?
Yeah, we have not used OPEs, and I think this is the next thing we are considering right now. I don't think it's obvious. So for one thing, OPEs in momentum space are not the same as OPEs in position space, and that's one of the complications. So usually when you do OPEs in position space, you assume that the two operators are close to each other, but they're not coincident. But if you now Fourier transform now to momentum space, you have to integrate over all space, so you cannot ignore coincident points. And that's one of the differences that comes if you look at the behavior of this functions kind of in the OPE limit.
Great, thanks. Maybe time for one more question if there is one.
So related to this OPE limit, so do you want to take large but not infinite momentum, or so how do you usually we take the OPE at close but not colliding points, right? Do you know how to separate those things?
Well, I don't think you can separate the two things. You say you have to take into account coincident points. You still want to take kind of large limit, but not infinite. But even in that limit, the leading behavior depends on the dimensions of the operators.
I see. And maybe a separate question, maybe a bit historical. So I was, for different reasons, reading this Pfefferman-Graham original paper. So there they were interested in building conformal invariants, right? So they go to this embedding space and so on. So what was Starobinsky's motivation?
I think Starobinsky wanted to know what is the more general kind of asymptotic anisotropic behavior in cosmology. It's a very kind of short paper. It's 2 pages, and I don't think it's as known as some of his other papers. It was certainly not known by Pfefferman and Graham, and it was certainly not known for almost 20 to 30 years. It was not known that the results were identical. But
did Starobinsky make this observation that could build conformal invariants out of this?
No. Starobinsky just wrote down this expression here, and he wrote down a formula for G2. And then he said, okay, these are the 2 pieces of data. And then he also said that G3 has to satisfy a conservation equation, but he made no other.
Okay, thanks.
And same thing for Pfefferman and Graham, right? So they wanted to discuss, of course, conformal invariance. But I mean, for them, this G3 was not the interesting piece. The interesting piece was, in a sense, what you can construct out of G0.
That's right.
In odd dimensions, actually, they set G3 to 0. So they kind of removed completely the physics out of the problem.
Right.
Okay. So Yeah, trying to keep us on schedule here. Thank you very much, Kostas. There's been another addition to the block of talks, Adam Bzowski, if you're here.
Yes, hello, I'm here.
Great. So if you want to say something quick or share some slides.
Yeah, so I will be very quick, hopefully, and well, thank you very much for ending me. So can you see my screen?
Yes.
Okay, good. So I have just one message. This is related to all this cosmology papers that me, Paul McFadden, and Kostas Skenderis worked on. And at some point in your life, you may need a 3-point function. And if it's a weird 3-point function, there is a good chance that one of us at least knows how to calculate it. So, I put all these mathematical procedure into a package that you can also download and play with. And so I just do one calculation for you because we discussed yesterday about some logarithms in 3-point functions, and this will be it. So the main point is that every conformal 3-point function pretty much can be written in terms of TripleK integrals. So these are this kind of integrals where you have 3 Bessel K functions and you integrate over some parameters. So this basically looks just like a Witten diagram. But the point is that you can also do it for tensorial correlators. So if you choose your favorite correlator, TTT, yeah, so you have a lot of equations. You have to decompose it into some tensor structure. So transverse traceless part has some tensor structure, has some form factors. But the main point is that when you deal with all this tensor structure, then all these form factors, you can, okay, I will not explain what that really means, but the point is that all these J's, these are these TripleK integrals, and basically in over even or odd dimensions, that doesn't matter, you can evaluate this. So you can have a complete explicit, it will be usually long solution. And so what I want to show you, I hope this will work. So I have this package here. And so this, what this represents, this is the basically a scalar 3-point function, conformal 3-point function in d dimensions. So the first parameter, okay, it's just d over 2 minus 1. And then there are these 3 parameters that represent just general dimensions. So you can see this is the so what this represents is just the integral of this mass over x. So there are 3 Bessel functions with some parameters, and now you can start substituting. So for example, one that's correlation function that's very prominent in cosmology is just 3 spacetime dimensions and marginal case. And I use some specific regularization here just to make things simpler, but you can shift these. I mean, this will diverge, so you have to shift these dimensions somehow. So this 3-point function, 3 spacetime dimensions, the same marginal operator is represented by this TripleK integral, and you can just evaluate it here, and you get this. So so Enrico, well, you talked about pretty much this correlation function, and you had this logarithm. So this is the logarithm, right? And then in your case, because it came from wave function, there was an imaginary part which was exactly proportional to this coefficient. So basically what that means in this language, so this is completely Euclidean. So all of this is Euclidean. It means that this correlation function has some scaling anomaly, which is basically given by this logarithm. So what I apply here is just you know, the dilatation, and of course this is the anomaly. So this is a local expression because it's proportional to the sum of 2-point functions. So in position space there would be a delta function. Okay, and so see, this is just, you can basically evaluate all these correlation function. And another one that we talked yesterday about is that you can, so here you have a single log, but in fact you can have also double logs, products of logs squared. And this, for example, happens in 4 spacetime dimensions when you also consider marginal operators. So the TripleK integral is represented by this. And okay, when you evaluate it, you get this long mass. So here it's long because it's not, you know, particularly simplified. But if you look at, so the thing is, this also diverges. There are some terms that you have to normalize. But when you look at the expansion in the regulator, so you get quadratic divergence, then you get linear divergence that already has logs, and then you have the finite part. And as you can see, this finite part here, it's not that bad. So this first piece, this is like the most non-local thing. So what this NL stands for, I mean, I'm sure you are familiar with this sort of polylog terms. So this NL just represents this polylog term. So this is like the meat of the correlation function. And then you have this mass. And okay, of course, mathematically I didn't write it very nicely, but if you look carefully enough, you will see somewhere here that you have squares of logarithms, these products of logarithms. Or maybe you can see, maybe you cannot. But one thing that you can do, you can again apply the dilatation operator. And when you apply it, you see that after applying the dilatation operator, you get logs in this expression, which means that the original expression had double logs. And physically, this is related to the fact that in this case, you have both anomalies and beta function. And in our papers, we explained how this is related to counter terms. And in fact, by classifying the counter terms, so you can write like, you can figure out like the most general counter term that you can use to make this correlation function finite. You can figure out what are all these scale violations and anomalies. So this is very nice because you can do all of that. And in fact, you can do all of that without even evaluating the correlation function, but also using our algorithm. This also in another paper, you can actually evaluate most of these 3-point functions. These are not very nice expressions, but if you want them, you can have them. So that's the message. Thank you very much.
Great, thank you, Adam. Any questions for Adam?
I do have a question. Sorry, just because yesterday I was interested in that simple example of the 3-point function for a massless scalar, because by unitarity, we demonstrated that the IR divergence demands the presence of an imaginary part of that wave function coefficient with precisely the same coefficient in front. Otherwise, it doesn't come from a unitary theory. But I don't see any I here, or maybe I'm not reading it correctly.
No, so there's no I here. So all of this is, so this is completely Euclidean. I guess you would need to suitably analytically continue these momenta, and then you would get an I.
Yeah, that's right.
So yeah, but you yes.
Yeah, that's right.
There's no scale in the log. I thought it came from the
no. So this is the So this is the regulated expression. So I had to put this regulator epsilon here, and so this is regulated expression. But as you can see, it's divergent. It has this 1/epsilon term. And now what you said is the fact that the coefficient of this log and this number are related. So that's the same statement as you made, but now for the regulated correlation function. Now to make it renormalized, you have to add a counter term, and then you will. So the counter term will have some scale to some power that's proportional to epsilon, just on dimensional grounds. And when you do it, you will remove this divergent term, but the scale will survive and it will exactly combine with this argument of this logarithm.
I mean, also, Enrico, you did a cosmological computation, so you need to use the holographic dictionary, what I was sketching in the beginning of my previous talk, and that contains analytic continuations and taking an imaginary part, and that's what is going to give the eyes that
yes, you can see the connection exactly. So the analytic continuation is momentum magnitudes go to minus I times momentum magnitudes, and then you take the imaginary part. So if you look at that log, all the p's go to minus I p's. That's e to the minus I p. So when you take the log, that generates a minus I pi with the same coefficient because it came from the log. So yeah, there's there's a sort of formula connecting genuine CFT correlators to de Sitter correlators.
I see. That's very interesting. So would it be correct to say that you're saying that the fact that the bulk evolution was unitary is contained in the fact that this thing is de Sitter invariant, because that's the only input here, or not?
I don't know. That would be interesting to study more.
Conformal invariant.
Yeah, that would be interesting to study more closely, looking at your paper. Yeah.
I guess you're also doing the analytic continuation correctly. That's what makes the time evolution consistent.
Yes.
That's where time evolution
continuation and then to use the de Sitter invariants.
Yeah.
Then,
so at least at level of a 3-point function, we have the correct analytic continuations. Yeah.
I see. Yeah. So there is probably some physical requirement that comes in when you connect these things to make it right. And the other comment that I wanted to make, maybe comment, you know, these things get much easier when you write them in terms of elementary symmetric polynomials, which is perhaps not too hard, but it just.
Well, yeah, of course, but I mean, this is because the 3-point function that you consider is symmetric, but I can
Yeah,
obviously.
absolutely. Yeah, exactly.
I mean, most of our papers, we did use that basis, the symmetric polynomials. If you go back to the 10 years ago, you will see that the expressions are given in terms of the symmetric polynomial.
Yeah, so this mass is also completely symmetric. So yeah, if you can, yeah, you can use symmetric polynomials. Yes.
I'm very confused about what was just said about analytically continuing the momentum. I thought we're in de Sitter, the symmetries are those of Euclidean conformal field theory. I thought the continuations, the i's that show up, have to do with deltas having imaginary parts and so on, but not continuing the p's. The p's are just as Euclidean in de Sitter as they are here.
Now, if you follow the holographic formulas we derived 10 years ago, you do need to do this continuation of the magnitude of the momentum.
You can view it either as Wick rotating the radius to a conformal time, or you can view it as continuing the momentum magnitudes, because of course they appear.
Sorry, I mean, aren't we just talking? Aren't boundary correlators and I mean, aren't the correlation functions in de Sitter Euclidean conformal invariant?
I mean, the relation is what I sketched in the beginning of the talk. So you have, in a sense, the triangle. You have the ADS, the CFT, and the de Sitter, and all of them are related. And okay, we did discuss in detail how to relate the three. So we start from, you can start from any point, go to any other one, but you do need to put, in a sense, the right i's when you go from one side.
Oh, I'm sorry. Here you have Bessel case.
Yeah,
oh, sorry. No, that's fine. Sorry.
Yeah,
sorry. No,
so what I wanted to say, if you do it cosmology, you have
sorry, let me just, independent of any representation, the symmetries that we care about for de Sitter are Euclidean conformal invariants, right? As a function of p's or x's. It's Euclidean conformal invariants.
Yep.
Right?
Yeah, that's
okay. But so then if we're writing down conformally invariant things, there's we don't multiply anything by I there.
I mean, the solution.
I thought the sort of i's have to do with the fact that it's not that the deltas can have i's in them. And
no.
For massive particles.
So
what happens in cosmology is that these Bessel case, if you do it in Hartle-Hawking state, these are Hankel functions.
Sure,
and then
sure.
you have, right, and you have specific contour. And when you want to do integral over this contour, is basically doing the Wick rotation.
No, that I'm perfectly happy with. I'm perfectly,
but it
okay,
puts I in front
here. Better. You mean in this particular representation, if you want to, but fine. Yeah, no.
Yes,
no,
and when you do that, you will get this imaginary part.
No,
right?
I'm perfectly happy.
This,
yeah, sorry, that's just what was bugging me. It's Bessel and not Hankel. And yeah, fine, no problem. But we all agree that it's Euclidean. I was just confused. It's actual, the actual correlators are Euclidean conformally invariant.
Yeah, this is, yes.
I mean, the solution that we have was a local solution without using any reality condition. Then depending on the context, you may choose to use different reality conditions. So
I got it. No, that's perfectly fine. Yeah, just, okay, thank you, sorry.
All right, so I think we should end the discussion section there. I'm told by the host we should take a 2-minute break between this discussion section and the one led by Nima. Is that still the plan B? I guess.
Yeah, let's breathe for a second. Yeah.